Okay, I gave my voice a bit of a rest, so this should be all the examples from section 1.6. I'm going to go over, just to give you an overview, I'm going to go over talking about a line that's parallel to something that passes through the point, or sorry, a line that passes through a point P and is parallel to another vector that we're given. I'm going to talk about this question where we find the distance between two lines. And then I'm going to answer this question, which of the following sets of parametric equations describes a line which passes through 2 points, P and Q. Okay. So, starting with this first one here, which of the following sets of parametric equations describes a line which passes through the point -1, -9, 8? I'm just going to go ahead and label that P0 because that is a point on the line. And my vector V, that is my direction vector. Here's the point on the line. Here's my direction vector. Because that's what it means for a line to be parallel to a vector, is that it's parallel, right? Here's that vector V, here's my line parallel to it. Right. Okay, so might as well leave that up actually. Right, then here's a P. Okay. That's the nice thing about vectors, right? We can just take this vector V and move it over here, right, for our uses. Okay, so starting with this equation, since we're in parametric form, I'll just go ahead and write out all the equations. Your book does not use A, B, and C here, but I find it more useful than talking about V1, V2, and V3, just because I want to avoid subscripts whenever I can. But hopefully you can distinguish between this ABC that I use here and the ABC that I use in the normal vector of a plane. But this one, if we plug in our values here, we get x equals -1, y equals -9, z equals -8. This is going to be -1t plus 10t and plus 2t. Okay, so right off the bat, if we can find this line here, right, if we find this exact set of 3 equations somewhere in our answer choices, then we are done with the problem. I say if, because we're probably not going to find that exact value here. In fact, looking for just one, -9, -8, no, I don't see those numbers anywhere on here. Okay, so we're going to have more work to do here. One thing I should note here is sometimes they will, for example, in this one here, they like to attempt to confuse you. 2 minus 3t is in the form that I like, but this would be -39 plus 30t. Right, see how they've changed the order. 14 plus 6t. All right, so just be on the lookout for that. They do like to change the order of these just to trip you up a little bit, so you're not just kind of hunting for the right numbers. Okay, so we're not finding any of these exact numbers here, but remember that we can define this exact same line with 2v. We could define this same line with negative v, right? So we don't have to pick that exact direction vector, negative 1, 10, 2. We could pick a lot of different ones. So let's look for some parallel direction vectors. So we've got negative 1, 10, 2. Maybe we can look for 1, 10, negative 2. We could look for 2, 20, negative 4. We could look for negative 3, negative 30, positive 6. All right, so these are just examples of ones we could potentially be looking for. Oh, what did I do wrong here? Oh, I guess that's fine. Sorry, negative 1, 10, 2. Oh, I see what I messed up here. Sorry. So this should be positive 1, negative 10, negative 2, positive 2, negative, negative, or this would be positive. Sorry about that. Okay. Right, negative 1 times this. Okay, so we can try just looking for some multiples or some scalar value, scalar multiples of this vector here, or we can kind of go through each option and see if it fits here. So maybe I'll just pick a random one to show you what that might look like. This direction vector is equal to, so this one, again, they've put it in a weird order, but this is going to be 1, 17, 4. 1, 17, 4, so not parallel to negative 1, 10, 2, which is what we need, right? So not parallel. Okay, so let's maybe hunt around for this. Let's hunt around for these and see if we can find any. This first one, 1, 17, 4. Nope. Negative. Well, we wrote it down here. Negative 3, 36. Potentially, right? This is good. 5, negative 32, negative 6. No, not quite. Right? 5 times that would be 50. So it can't be that one. Can't be that one. Can't be this one. 3, 27, 24. No. Negative 3, positive 36. Oh, potentially. And then 5, negative 32, negative 6. No, won't work. Okay, so it's in between these two. Let's test. Let's test B. So what that means is we're going to be testing the point Really what we're after is we know that the direction vector is good. We just want to test 2, -39, -14. All right, see if that works out. All right. So when we test our line here, we're going to get 2 equals, that's our x value, -1 minus t. Here we're going to get -39 is equal to -9 plus 10t. -14 is equal to -8 plus 2t. And again, for testing out a point, we're going to see if that point is the same. Or sorry, if that t value is the same for all of these. So let's see, t in this case is going to be equal to, so -1, that would give us 3. So t is going to be equal to -3 in this case. T in this case, we get, looks like t is also equal to -3. And in this case, let's see, +8 is going to give us -6 divided by 2. T is equal to -3. All three of these line up. So looks like that point is on the line. We took care of our direction. We took care of our point on the line. So if this has a point that's on the line and it's got the right direction, this is our answer here. Right? If we test this one, we only get one answer option here, but this will give us different t values when we test out the point 4, 36, 32. Okay, so that takes care of the first one. This one, just to change up the pace a little bit, we are going to find the distance between these two lines. So again, the process here is we're going to figure out two parallel planes that contain these 2 points. We're going to find a normal vector that sort of connects them, and then we'll just measure the distance between those 2 planes. Okay. So I'm gonna leave this. Well, I'll erase it for now, but I may bring it back in just a second here. But I do want to figure out these. I do want to figure out these vectors first on here. So let's say this line. Let's start with this orange line. Call it line 1 and line 2. I think this is the easier point to figure out. We're gonna have to figure out both of them, but I'm gonna use this as my P naught. For this line, and then my direction vector is just going to be that. All right, starting from P naught. So coordinates for this point are going to be so in the x direction, that's 4.5. Right, because they're telling us that it's on the corners or midpoints. So 9 would be the full distance, so half of that would be 4.5. That's in the x direction. I'm not traveling in the y direction. I'm not traveling in the z direction at all. Get there, so that's 0, 0. Maybe I'll use that for my p naught. Actually, I like that a little bit better. I'll use that for my p naught, just because it's got a lot of zeros in it. Okay. This line here, however, is going to be, this point here is going to be, looks like the upper corner of this box. So if I think about the dimensions, 9 by 7 by 6. All right, 9, 7, 6. That gets me all the way up there. Okay. So for line 1, P naught is going to be equal to, so I decided I liked this one a little better since it's got zeros in it. And my direction vector is just going to be the vector between these 2 points here. So that's going to be, I'll count it like this. I'll say that direction there. So let's see, that will be vector 9 minus 4.5. 7 minus 0. And 6 minus 0. So that's going to be the vector 4.576. Yeah, I'm happy with that decision. Okay. For line 2, again, I'm not thinking about these parametric equations yet for these 2 lines. I just want to get my direction vectors mostly. So let's call this one here, maybe we can call this Q naught, just to give it a different name. So Q naught, let's see. In the x direction, looks like it's traveling 0. In the y direction, well, let's go z first. So 0 in the x direction. In the z direction, from the origin, we're traveling up 6, and then over halfway. So half of 7 would be 3.5. So 3.5 in the y direction, 6 in the z direction. And this point over here is going to be, let's see, well, one way to think of this maybe is that it's got the same y and z coordinates as this point here. We're just kind of moving it. Oh no, it doesn't. It's moved over 7 in the y direction, 6 in the z direction. So 6 in the z, 7 in the y, and then halfway for the x, which is that same 4.5 there. Okay, so the vector for this one, let's call this one, let's call it w, right? Just to give it a name. Let's go this minus q naught, so let's go this vector in this direction. So 4.5 minus 0, 7 minus 3.5, and 6 minus 6. So that'll give us 4.5, negative 3.5, or sorry, positive 3.5, and 0. Okay. All right, that normal vector between them, so maybe I'll draw it this way. Maybe I'll draw it again. I've got two planes. Those two planes are parallel to each other, and they're connected by this normal vector. Right? That normal vector is going to be the distance between them. But in terms of making these planes here, the plane I'm interested in is going to have a normal vector that looks like this. So V crossed with W. I'll go ahead and do it by hand, right? So we get 4.576, 4.5, 3.50. My y is going to be 0 minus 6 times 4.5. And my z vector is going to be 4.5 times 3.5 minus 7 times 4.5. Again, no judgment if you want to use the calculator on GeoGebra. So let's see. This is going to be negative 21. This is negative 27, but it's negative that, so positive 27. And then this one, I'm going to cheat and use the calculator here, negative 15.75. Okay. So there is my normal vector between these two lines. So the equation of these two planes plane 1 has a normal vector negative 21, 27, negative 15.75, and a point on it, 4.500. Right, I can reuse it from the line, because if it's on the line, it's on the plane that we made. Let's go ahead and figure out that equation there. So this is going to look like, I'll use that AX plus BY plus CZ form. So negative 21x plus 27y minus 15.75z is equal to D, which is my AX naught right, plus 0, right? Because we've got, well, I'll be a little more exact with this one, even though. Okay, so that's going to be, let's see, 27 times 0 plus negative 15.75 times 0. Right, so in the end, I get negative 21x plus 27y minus 15.75z is equal to whatever 21 times 4.5 is. 94.5. Okay. Great. So that's plane 1. We'll repeat the process for plane 2. Plane 2, same normal vector. Negative 21, 27, negative 15.75. Just move this out of the way here. There, that's a little easier to read. Okay. And my point that I'm going to use here, I think I decided I wanted this to be 0, 3.56. So, negative 21x plus 27y minus 15.75 z is equal to, this time around we've got negative 21, so our d value, negative 21 times 0 plus 27 times 3.5 minus 15.75 times 6. Again, if you're in a race with somebody trying to figure this out, you can just take the you can just take finding this d value. You don't have to rewrite this every time, but I do want to show you where in the equation this is coming from. Okay, so this is 0. Let's see, 27 times 3.5 is 94.5. I think I knew that. Is that right? 21 times 4.5 is the same as 27. Yeah, okay. Makes sense. So 0 plus 94.5 minus 15.75 times 6, which is 94.5. Oh, they were very generous and gave us something that equals 0 here. Okay, great. So, so this vector here, sorry, the plane that we get is negative 21x plus 27y minus 15.75 z is equal to 0. Now we're cooking. Now we've got d2. Well, let me organize it this way. So I'm just going to do a little rearranging here. Just make sure everything fits on the page when you're reading it later. So a big conclusion from this one is that this is, we could say that D1 is equal to 94.5, and D2 is equal to 0. Awesome. Okay, the distance between these two lines, or these two planes, however you want to think about it, is not 94.5. We do have a match here, which is good. We have negative 21, 27, and 15.75, which is great, but we want to use the following formula. So we'll say this distance here is going to be equal to d2 minus d1, but the idea was that these are supposed to be in normalized form, where we find a normal unit vector that has a magnitude of 1, but the way to fix that I mentioned in the other video is to just divide it by the normal vector there. So anyway, let's find the magnitude of that normal vector. So the magnitude of the normal vector is going to be equal to square root of 21 squared, or negative 21 squared, plus 27 squared, plus negative 15.75 squared. So once we get the square root of all that, that'll be the magnitude of our normal vector. Okay. So 21 squared is 441. 27 squared, 729. And then 15.75 is 248.0625. Six there. Okay, just add these up really quickly. 441 plus 729. Okay, 1418. .0625. Let's see if this just square roots to something nice on its own. Yeah, it's around 37.657. You can leave it in this form, but I'll say it's around 37.65. Great. Okay. So two planes, distance between them. This magnitude of the normal vector looks like this, so our distance, we made it. Luckily we can count on that absolute value, giving us a positive number when we need it. So this is 94.5 divided by 37.65 approximately. So that's going to be 2.51. So distance between those planes, 2.51 just about. Distance between these lines, 2.51 just about. Okay. This one will be a welcome break after that one. All right, so just back to parametric form. A line that passes through P and Q. So here we'll kind of use, we haven't seen exactly this, but we can intuit, right? If you watch that theory part of the video, you can understand exactly where we're coming from with this. So here's P, here's Q. Let's use Q as our P naught, because why not? Right, because that's a point on the line, so why not use it? And then if you want to make a direction vector on here, here's a good one. Right. This vector here, QP. So I'll just do a very symbolic version of this. So our direction vector is going to be equal to QP. Which is going to be, let's see, so P minus Q. So 3 minus 0, negative 8 minus parentheses negative 9, and negative 2 minus 5. So our direction vector is going to be equal to 3, negative 8 plus 9 is 1, and negative 2 minus 5 is negative 7. So 3, 1, negative 7. Okay, which of the following sets of parametric equations describes a line which passes through the points this and this? Well, whatever line we find has to have something that has a line that looks something like this. So let me just double check that I did everything right here. So negative 8 minus negative 9, negative 2 minus 5, 3 minus 0. Okay. So we are looking for 317. We are looking for 317. We're looking for negative 3, negative 1, positive 7. We are looking for negative 6, negative 2, positive 14. We are looking for, let's say, 9, 3, negative 21, etc. Right? Any scalars of this direction vector, right? Because they could describe. We didn't have to use this exact direction vector. We could have used this one back here. Okay, so let's take a look. Negative 12. Now, what's the y component here? Because we don't have any t here. So this would have a direction vector negative 12, 0, 21. Right. Negative 12 from the x, 0, 21. Okay. So anyway, definitely not what we're looking for here. So that's not it. What about negative 3, 8, 2? No. Negative 12, 0, 21. No. Negative 5, negative 3, 14. Negative 5, negative 3, 14. Closer, but not what we're looking for. Negative 3, negative 1, positive 7. Here we go. Right now, this is the only choice that we have, which is great for us, right? We can just pick it right away. If you continued down this list and you saw another one that had that same point, or that had a parallel direction vector to this line, you'd have to test that point out. So a way to test that might be, I would use this point here. So I'll say this. This is the only parallel. Or I'll say this is the only choice with a valid direction vector. Oh no. I'm stuck in this weird scroll wheel setting. Get me out of here. Oh my gosh. Sorry, I had to wrangle that loose. So this is the only choice with a choice with a valid direction vector is E. All right. If we want to double check, or if we have multiple options with valid direction vectors, we can double check the point. 6, -7, -9. In our line, which we didn't write the equations down for, but we could say x equals 0 plus 3t, y is equal to -9 plus t, and z is equal to 5 minus 7t. Right, just using the parametric equations of the line. So we would just plug in 6, -7, -9, and that would give us the values that we want. Okay. That is definitely enough for quiz 3. If you can solve these 3 problems, you'll be set for quiz 3, and nearly everything for test 1. There's one more problem I want to show you, but I'll do that in class when I'm feeling a little better. Okay, I will talk to you soon. Take care.